So today's topic is loss functions in neural networks and deep learning, deep learning algorithms. Now, where does this loss function comes? Now, actually, in the last class we have discussed the neural network training. Okay, so here is the diagram which shows the training procedure in neural network. Now, here, suppose this is a neural network having x input and theta parameter input. Now, what is theta? We have discussed in the last class. So, this theta contains neural network weights and bias parameters. Now, every neural network, see, you can see here. So, we have discussed in the last class. Just a second. See, in this neural network, you can see here that there are some associated weights with every input. See, W1, W2 up to Wn. So each input has got its own weight parameters. So x1 will be multiplied by w1, x2 will be multiplied by w2, and so on. So each input path is associated with corresponding weights. Now, similar to that, each neuron will be given with a bias. Okay, so these things we have already discussed, and we have seen the equation also. So here also, see, each neural network will contains some uh, weights and some bias terms associated with. Okay, so these weights and bias terms we have taken here as the theta parameter. Okay, so theta parameter contains weight terms and bias terms. Okay, if there are different neurons, then there will be different bias terms like b0, b1, etc. Okay, now you know that weights are numerous in number. Okay, depending upon the number of neurons, and each neuron has got different inputs. Okay, so there are a lot of weights also available. Now, combinedly, we are calling these weights and bias parameters as theta. We are denoting these parameters as a single parameter theta. Actually, it is not a single parameter, it has got different parameters inside that, like weights of the neural network and bias terms also. Okay, now assume that we have the neural network here with input as x and parameter vector as theta. Okay, now when we give x input, x contains x1, x2 up to xn. Okay, so when this neural network is given with an input, you know that it will produce an estimation, an output, maybe prediction or classification. Okay, so that we have already seen in the previous session. So, like we have seen this particular implementation, a sample implementation of a handwritten digit classification we have seen, isn't it? Now, whenever we give input, it will produce some output, some estimated output. Now, similar to that, here we will get an estimated output. Okay, now that output is y cap, which will be a function of input and parameter. Okay, so that output will be compared with the actual output for this corresponding input. Okay, so this y is the actual output, this y cap is the estimated output. Now the difference between actual, so that difference means it's actually a function. We have different functions. Okay, now this function is known as loss function, which is actually an error function. So which calculates the error between the actual output and the estimated output. That error value is denoted by using error function is denoted by using loss function. So this is the loss function. L of y cap comma y. It is the loss function. Now, what is the next step? We have seen that this loss function we will optimize in such a way that we will get minimum loss. Then only the training will be proper. Now, what is training? Training means we are making the neural network able to classify or predict according to our input and output. Okay, so that means we are training the neural network. So we are giving the actual input to the neural network. We have the actual output here. Now the estimated output will be compared with the actual output. Then we will find out the loss or the error between the estimated and the actual outputs. Now, what is next step means? We will try to make this loss function reduced in such a way that the difference between actual output and estimated output is minimum. So that means, in other words, we can say that we will optimize the loss function in such a way that the difference between actual output and the estimated output is minimum. Now, how will you do that? Now, in order to minimize that, what is the actual procedure means? So we should see x cannot be varied to the neural network. X cannot be varied. X is fixed. X is the given input. Now, what we can vary? We can vary the parameter theta. Okay, so this loss function will be optimized by varying the theta. Okay, that's all. So this is the actual process in training of a neural network. So this will happen during the back propagation. So why it is known as back propagation? What is forward propagation and what is backward propagation? So forward propagation means, see here you can see input is given, it will produce the output. This is known as forward propagation. So just a second. Okay, so here input is given. Using the neural network, we will find out y cap. This is a forward propagation. Forward propagation. Okay, so this process, once this process is over, we will find out the loss function. Now we will do some optimization algorithm on it, and we will find a new value of theta. Theta is. So this particular process is actually we are propagating or we are changing the theta now in the backward direction. That is why it is known as backward propagation, back propagation. This theta was already there. Okay, now we are changing that theta already that was present there. No, in a in the backward fashion, or when we that means we are going from the output to the input side, backward propagation. Okay. Now, the optimization and all we will discuss later. For the time being, we will see what are the different types of loss functions available. Then only we can study the optimization. See, here we have the procedure for optimization. We will see it later. Okay. Now, different loss functions. So just now we have seen we have the actual output. Say it is yi. Sorry. Okay. Say it is yi and the predicted output corresponding to yi. Now the I varies between 1 to n. See, you can see here you have x1, x2 up to xn, isn't it? Now corresponding to, sorry, um, okay, that is enough. That is enough. Okay. Now, for a particular sample, you have an output. Assume that this is the actual output, and this is the estimated output. Yi cap. Now, this loss function, the first type of loss function is mean square error. Now, we have already learned mean square error while we discussed the linear regression in the machine learning class. Okay. Now, mean square error means we will find out the difference between actual and the predicted or the estimated output. then we will take the square of that, then we will sum it up for all the samples, then we will divide the summation result by the number of samples. Okay, so that is mean square error. We are taking 1 by n, that is why it is mean. We are finding out the mean. Okay, so here we are taking the squared error. That is the meaning of mean square error. Okay, so this mean square error is a loss function. Now, this mean square error will be mainly used while we do the regression task. Okay, while we do the regression task using neural network, we can use this mean square error as the loss function. Okay, see this L of y cap comma y or L of y comma y cap, both are same. Okay, so this particular loss function, which is known as mean square error or squared loss or L2 loss, okay, is used in regression task. Okay, regression type of operations only using machine learning. Machine learning also it is there, and in neural network also. If you want to have some regression task, you can use this mean square error as the loss function. Okay, now for classification problems like the binary classification, multi-class classification, we have some other types of loss functions: binary cross entropy and categorical cross entropy. So cross entropy is the loss function used while we deal with classification problems. Okay, so for binary classification, we will be using a loss function named binary cross entropy loss function, which is also known as log loss. Now, here is the equation for binary cross entropy. We are not going inside the details of this equation. Uh, for the time being, assume that this is the equation used for finding out the binary cross entropy. This is actually not a difficult equation. See here, we have again that here one minus signature is there, minus sign is there, then we are finding out the average here, then again the same summation. See yi into log yi cap plus 1 minus yi into log 1 minus yi cap. So this is the equation used for finding out the uh, binary cross entropy, and it is used in binary classification problems. So here an example is been shown. So this one we have already discussed. So this is a type of binary classification. See, you have different inputs here and input layer. Then a hidden layer is there. Then in the output, see we have only one neuron. So output will be only one or zero, or we can say yes or no. So this is a type of binary classification. An example, cancer prediction, a cancer prediction task. Cancer. The output will be, what will the output of the cancer predictor? Cancer, yes or no. That means one or zero. Output can be only one or zero or yes or. So that type of prediction is known as, sorry, the classification is binary classification. And this type of classification we can use this binary loss function, the binary cross entropy loss function. Okay, so the binary cross entropy loss function is used for binary classification problems, like we have discussed just now here. So as we can see here, here there is only one neuron in the output layer. Okay, see, in such cases, the output layer has only a single neuron with a suitable sigmoid activation function. Now, we have discussed in the last session where we discussed the different activation functions. At that time, I explained what is sigmoid activation function. and the sigmoid activation function is used for binary classification only. I have discussed that. Okay, so in this scenario, we can use binary cross entropy as the loss function. What is the scenario? Here, at the output layer, we have a single neuron only. So, single neuron means we will have binary classification 1 or 0, yes or no. And the output layer has only one layer, and that layer use sigmoid activation functions. In this scenario, we can go for this binary cross entropy. So this is a second type of loss function. So first type of loss function we will be using in neural network is the usual mean square error. Mean square error can be used in regression task only. Okay, so we have already studied. Then the second type of loss function is binary cross entropy. The binary cross entropy we can use for binary classification problems, and in those kind of problems, we will have only a single neuron at the output layer, and there the activation function will be sigmoid activation function. Okay, now in multi-class classification, so that means assume that instead of this single neuron, we have multiple neurons at the output. See here, one more output. Here, one more output. We have multiple neurons. Now, see here, there are three neurons at the output layer. Like that, every neuron will be interconnected. Okay, so we have three different neurons at the output layer. Now, for example, you have a multi-class classification problem like the problem we are going to discuss in the next class. That is cat, dog, human classifier. Cat, dog, human classifier. Okay, so there are three classes. Okay, so definitely there should be three neurons at the output. Okay, so we will discuss it during the next class. Okay, so there will be three different neurons. So this is a multi-class classification problem. Now we need to classify the given image. The input at the input we will be giving an image. Okay, so this image contains cat or dog or horse. So that is the problem. That is multi-class classification problem. Now, as an example, we have already discussed the handwritten digit classification. So in that also we have seen the multi-class classification. See, so here we had, see, this is handwritten digits means we will have 10 digits, 0 to 9, 10 classes. At the output, we will have 10 classes. So there will be 10 neurons at the output, 10 neurons. Okay, so from 0 to 9. This we have already discussed. Okay, so there is no need to explain it again. So there will be 10 different neurons at the output level. So this type of classification is multi-class classification. Now, in that scenario, we can use categorical cross entropy. See, categorical, different categories are there. Okay, now during this categorical, that means if there are multi-class classes available, then as I said, we will be using softmax activation function. The activation function that we will be using is softmax. Instead of sigmoid, we will be using softmax activation function. So that also we have discussed. Actually, there is nothing. So we have different activation functions. Each activation functions has some or its own applications. Okay, and as I discussed, the activation function used for binary classification is sigmoid. The activation function used for categorical or multi-class classification is softmax. Simple. Okay. Now, in this scenario, the loss function used is categorical cross entropy given by this particular equation. Now, as we have, as the discussion of the categorical cross entropy equation is not intended here, I am not discussing it. Okay. Now, the derivations are available. Derivations are available. You can have the derivations straightly by looking at the websites. Okay, or even I can provide the derivation also. Okay, but that is not important for our purpose. So I am skipping the derivation. Okay, so this is the equation used for the loss function when it is categorical cross entropy loss function. Okay, so in multi-class classification, the last neuron we will be using softmax activation function. That's so. So these are the different active loss functions available in neural networks. Now, where does this loss function comes? As we have discussed, the loss function is the function which find out the error between the estimated value and the actual value. Okay, so that is the loss function in order to find the error between the difference between estimated output and the actual output. If you find the estimation, then only we can train the neural network in such a way that the difference between estimated output and the actual output is negligible. Okay, so that is the process. Now, how we will make that uh, loss function optimized, or how we will minimize the difference between the error between y cap and y. Now we have already seen that that error function can be defined in three ways. It can be defined in according to this equation, the ms equation. It can be defined according to this equation. If it is a binary classification problem, the loss function can be defined by using this equation if it is a multi-class classification. Okay. Now, how we will, next one is how we will optimize the function, how we will optimize this loss function in such a way that the difference between y cap and y is minimum. Okay, so that is the task we are going to see. Okay, so that means uh, optimization algorithm. So we are going to see some of the optimization algorithms. Now, before moving into optimization algorithms, what is optimization? For example, you take a function f of x is equal to x squared. Assume that we have a function here, f of x is equal to x squared. Now, optimization means finding the value of x, finding the value of x in such a way that it minimizes the function. Okay, finding the value of x in such a way that it minimizes the function output. That means x squared. Okay, now if you plot a curve like this, at what value of x this function produces minimum output or this function minimizes? Now you can see for the value of, see here x-axis is x and y-axis is f of x. Now if x value is equal to 0 or for x value is equal to 0, you know that the output is going to be 0. So that is the minimum value. So that means for this particular value of x, that is x is equal to 0, we will get the function minimized. Isn't it? Now for all other values of x, what will be the function output? Say for minus 5, what will be the output? Minus 5 you have to give here. Now minus 5 square, 25. So function output is 25. Similarly, for all other values, you will be getting function output which will be greater than 0. Okay, so the minimum value of the function will be 0. That we will get for x is equal to 0. So this particular process is known as optimization. Finding the value of the parameter So here the parameter is x in such a way that that function is minimized. Output the minimum value. This particular process is known as optimization process. Now, in our case, what is the function to be optimized? In our case, the function to be optimized is the loss function. Okay. Okay. In our case, the function to be optimized is the loss function. So before that, any doubts up to this? So this is actually an important uh, topic. Now we can you can skip it, but in order to explain the working of the machine learning algorithms or the neural network algorithms or deep learning algorithms, the knowledge of these topics, the information, what is available here is very much important, very much required. Then only you can explain the algorithms properly. You can skip it also, no issue, but the complete explanation you can give if you know these topics. Okay. Now here our the function to be minimized is, let us take it as j of theta. The function to be minimized we will be taking as j of theta. Actually, we have the function which is loss function of y comma y cap. Okay. Now you know that it's actually a function of theta, isn't it? So because you know the importance of theta here. So this theta actually determines this y cap, isn't it? So for simplicity, we will take the function to be minimized is j of theta, some cost function, some loss function. So this function is known as a loss function or cost function, j of theta. This is loss function or the cost function. Both are used interchangeably, but both are not same. But for the time being, assume these two are almost same. Okay, so anyway, we are going to minimize this cost function. Okay, for example, you take this uh, mean square error. For example, take the loss function, which is the mean square error. Okay, that we have represented here as j of theta. And we have represented here as j of theta. Okay, now you know this is the plot of g of theta for different values of theta. Okay, so this particular curve actually gives the plot between theta and j of theta. What is theta? Theta is the parameter to be okay. Theta is the parameter to be updated. Now for different values of theta, we will get different loss functions. For different values of theta, we will get different loss functions, and assume that when you connect all those loss functions, we will get a curve like this. Assume that you will get a curve like this. Okay. Okay. So the function to be optimized is j of theta, and for different values of theta, assume that you are getting a curve like this. Now, actually, what is the minimum loss function? See, you know that from the graph itself. See, this particular value of theta gives the minimum loss function. So, this particular value of theta we should find out. Okay, that is optimization problem. So, here we are making use of gradient descent algorithm to find the optimum value of theta. So this is the first type of optimization algorithm, gradient descent optimization algorithm. Okay, you got the point. So as I told you, we need to optimize the loss function. We need to optimize the loss function. Say here loss function is j of theta. We need to optimize the loss function, which is j of theta, or loss function of, I will write clearly. Actually, our loss function is j of y comma y cap. So we need to optimize this function. We are representing this function as j of theta. That's all. Okay, so we need to optimize this function. So that means we should find the value of theta in such a way that this j of theta is minimum or optimized. Now, for that, there are different algorithms like a stochastic gradient descent. See, gradient descent is there. Then we have stochastic gradient descent. Then we have Adam. Then we have RMS prop. So these are the different optimization algorithms we are going to see now. The first one is gradient descent. Actually, this stochastic gradient descent is actually a modified version of the first version, that is the gradient descent. Okay, in gradient descent, we are going to optimize this. Now, as I explained previously, we have plotted the j of theta against theta. Okay, now in gradient descent algorithm, we will minimize the cost function where theta represents the parameters. We will minimize the cost function j of theta. Now, what are the steps? Now, first of all, this is actually important. First of all, we will give an initial value of theta, theta 0, an initial guess. It is a random value. Now, we can have initially 0 or some 1, etc. These are not the exact value. Any value you can give. That's initial random guess we will be giving as theta 0. Say this is the starting point. So this is the value corresponds to theta 0, starting point. Assume that this is starting point. Now you can have here also starting point, no issue. Okay, that is up to us because we are selecting it randomly. Initial guess. Okay, now this is the starting point. Now our aim is to arrive at this minimum, optimum value. Now how will you proceed? That is the second step. Now the second step is compute the gradient of j of theta. That is delta of j of theta. So this is actually I have already presented here in this diagram. See, we have the loss function here. Now we need to take the gradient of the loss function. Here the loss function I have represented by L of theta cap comma L of y cap comma y. So gradient is delta of L of y cap comma y. Now here the loss function we have represented by using j of theta. So the gradient of j of theta is delta j of theta. Now gradient actually means a differentiation. Gradient actually means the derivative or the slope. Okay. Now, what is second step? Initially, we have defined the theta 0. That means the point here. Theta 0 is the first point. Now, our aim is to find out the theta such a way that for that value of theta, j of theta is minimum, isn't it? So, we should proceed from here to here. Now, for that, first thing is take the derivative at that particular point or take the gradient of this j of theta at this particular point. This point, the starting point. That means we are finding out the slope. We are finding out the slope. Derivative means we are finding out the slope at that point. Okay, so that is the gradient. Gradient of j of theta at that particular point we need to take. That is dj of theta divided by d theta. Now, in practice, this theta, as I told you, has multiple parameters like different weights W0, W1, W2, etc., and different bias terms B0, B1, B2, etc. Okay, so there will be different terms in theta, uh, like theta 0. Theta 0 may be the W0, then theta 1 will be there, it may be W2, W1, then theta some 5, it may be the B0 bias time, etc., etc. Okay, so it will be a vector like this. Okay, so that means there will be different parameters inside this theta. Now in that case we need to go for partial derivative. That means if there are multiple parameters, so the gradient will be a vector. Gradient will be a vector of partial derivatives with respect to the parameters. That means dou j theta by dou theta 0, uh, dou j theta by dou theta 1 up to dou j theta by theta n. Assume that there are n parameters. Okay, so this will be the gradient of the loss function delta j theta. So that we have already calculated here in step number 2. Assume that we have calculated the gradient of j of theta in step number 2. Okay, so that means we are doing this particular step here. We are finding out the gradient. That means gradient of loss function. Now the next step is actually the updation step. Okay, so that step we will discuss as the third step. In between, we have some information that we are skipping now. We are not discussing these things now. Okay, so for the time being, understand we have the loss function plotted here. Now we have the initial value of theta. Second step is find out the gradient vector. Why it is a vector? Because we have different parameters, so it will be usually a vector. Partial derivatives like this. Okay. Now, by default, the gradient actually, the output of the gradient will be a vector from the basic mathematics. Gradient means it's a vector. Okay, anyway, now we are moving into the update step. That means the third step, updation of parameters. That means we need to find the new value of theta, theta t plus 1, which is equal to the previous theta minus some scalar quantity, some multiplying factor alpha into the gradient. Okay, the previous gradient. That means the gradient we have seen here. Okay, that's all. So this is the update parameter step. That means here we are finding in the new theta. How we will find the new theta using this equation? The new theta is equal to the previous theta, the current theta minus the gradient of the loss function we have calculated just now multiplied by this scalar quantity. So this scalar quantity is actually known as learning rate. So we will discuss it later. Okay, now so that means what is actually happening is, so you can see here initially the starting point was here. Now when you do this calculation, that means we are minusing the gradient value. That means we have a magnitude here for the gradient. Okay, that magnitude when we are minusing from this previous theta value, we are actually what is happening is we are moving the theta value to a new theta value. For that theta value, okay, to a new theta value, theta t plus 1. It was theta at t, now it becomes theta t plus 1. That means here theta t plus 1. Now, what is this learning rate or this scalar quantity alpha means? We are multiplying the gradient value, the magnitude of the gradient by a scalar quantity moves, which actually moves the previous value of the gradient from this position to this position. So this particular, see this uh, variation, so this is known as the step size, this incremental step size. Okay, so this is actually determined by this multiplication factor. Now you know that when the factor increases, the value which is actually minusing from theta t will be increased. Okay, depending upon the value or decrease. See, if it is 0.01, it will be decreased only. Okay, so that means by varying this alpha, this new parameter can be, that means the change can be varied. The difference between these two, the old parameter and new parameter can be varied. So that is actually determining the step size. Now here, assuming that, for an example, for easy understanding, assume that this value is the gradient value is 2.5. Assume that the gradient magnitude is 2.5. Now assume that the alpha value is zero point zero 0.01. Assume that the alpha value is zero point zero 0.01. Now when you multiply 2.5 by zero point zero 0.01, you will get 0.025. Okay, so that means from the previous value of theta, 0.025 will be minus, isn't it? So that means we are getting a new theta. New theta will be in this direction only. Okay, so that 0.25 actually means this much difference. So that is determined by using this alpha. That is why this alpha determines the step size. Okay, now I think you understood the point, isn't it? Now the concept is simple. Now we need to get a new theta value by using this update equation. Okay. Now, if you vary the alpha value, see, assume that you are giving a too large alpha value. Now, if you give it too large alpha value, what will happen? See, the step size will be more. So that means, see, the theta value will vary between or change from this value to this new value. Now, since the alpha is large, the step size is large. Step size is large, isn't it? Now, what is the problem with this large step size? Now, here itself you can see actually the minimum value should be here. Now, if you follow this step size, whether we can reach the, see, from here, the next step size will be to here. Now, we won't be able to reach the minimum value, optimized value. That means overshoots the minimum. So that means, again, if you vary, it will come here, somewhere here. That means it will overshoot or it will go here using the step size. Now, since the step size is large, we won't be able to go into the optimized value of theta. Now, if the step size is small, that means only a small change is happening. Now, here you can go to the minimum value, but the problem is it will take too much time. Learning rate takes forever. Okay, that means learning will take a long time. So, this is also not acceptable. Too small learning rate is not acceptable. Too high learning rate is not acceptable. So we should have a compromise between these two. Okay, so this is the actual process. This is the actual importance of this learning rate. Alpha. Alpha is actually important, but we should select in such a way that it should not be too large or too small. Okay, I will be giving you the range in which we can give the learning rate when we have the hands-on in the next session. Okay, so this is the next step, the update. Okay, that means just now I have shown here. So here, so here we can see the update operation takes place. We are getting a new value of theta, and we are varying this theta. Again, we will find out the y cap. Again, we will find out the loss function. Again, we will optimize the value of function, loss function, in such a way that a new theta is obtained. Now, it will repeat. So, we will have so many iterations. Okay, so this is what is happening in neural network training with the use of optimization algorithms. Okay, so this is the gradient descent optimization algorithm. The last step would be repeat step number 2 and 3 until convergence where the change becomes very small or cost function reaches satisfactory minimum value. Okay, satisfactory minimum value of cost function, if it is reached, then this process will be terminated. That's so this is the uh, gradient descent algorithm. It is actually simple, but anyway you don't require these things when we have the hands-on. Hands-on you will be using the just a line of code will give you the operation. Anyway, we are not going to use this gradient descent because this gradient descent has got some disadvantages, it will take. See, the main problem is it is expensive to calculate the gradient if the size of the data is huge. Now, as I told you, now we have to repeat these steps. Now, we have discussed the gradient descent. We have seen there are different steps. Step number 1 is there, step number 2 is there, step number 3 is there. So step number 2 is computing the gradient, step number 3 is computing the updation. Now, repeating the step number 2 and 3 until we will get a satisfactory minimum value of theta, j of theta. Now, if the number of samples are very much high, the size of the data is huge, then it will be too expensive to calculate the gradient, and the other operation is also time consuming. So that is the main drawback with gradient descent. Now, in order to overcome that drawback, we are having one more algorithm, that is a stochastic gradient descent. It is actually an updated version of gradient descent, that is stochastic gradient descent. Okay, now it is also simple. Now here, instead of taking the all number of samples, that means assume that you have 10,000 samples, 10,000 images or 10,000 records, assume. Now instead of taking each sample one by one and calculating the minimum value, so that requires more time. So if there are 10,000 number of samples, what will happen? This process takes more time to compute, isn't it? Because we have to repeat step number 2 and 3 until the convergence happens. Okay, so that is actually time consuming. In order to overcome that, in stochastic gradient, it is actually a variant of gradient descent where parameter update is computed using a small random subset of the training data. Instead of taking the full set of data, we will taking a small random subset, a mini batch, we can say. A mini batch will be taken rather than the entire data set. The process remains same, but the we will not be taking the entire data set, but we will taking a mini batch only. Now you know that if you take a smaller number of samples, then the computation time can be saved. So that is the process in stochastic gradient Then we have RMS prop. It is again a variant of stochastic gradient descent that adapts the learning rate using a moving average gradient, squared gradient. So anyway, we are not going to discuss, but you at least know we have this RMS prop algorithm available for optimization, which is actually an advanced version of stochastic gradient. Now, commonly used optimization algorithm is ADAM, which is also an extension of stochastic gradient algorithm. Now, here the advantage is ADAM optimizer dynamically adjust the learning rate based on individual weights. See, the learning rate will be adjusted dynamically. Now, in gradient descent, the problem is the constant step size. Now, if you select a step size, it will be constant. But in this Adam algorithm, advantage is it dynamically adjusts the learning rate based on individual weights. Okay, so that is the advantage of this Adam optimizer. That advantage is there in RMS prop also, but the Adam algorithm will perform better than the RMS prop. So that is why the Adam optimization will be most commonly used in neural networks and deep learning also as optimization algorithm. Okay, so the detailed discussion of this RMS prop Adam is actually out of the scope of this discussion. Now, if you want, you can have the all the details available in websites. Okay, but in my opinion, don't go into that much details. No, you at least be aware that you have these many uh, optimization algorithms, and out of these, Adam performs well. At least that point you understand. Adam performs well compared to other algorithms. RMS prop is also okay, but comparatively, Adam performs. But again, it depends on the situation. It depends on the input data. In some of the input data, Adam performs better. In some of the data, this RMS prop performs better. In some of the data, stochastic gradient performs better. Okay, you can vary the optimization algorithms uh, by your own, and you can verify the result. That's all. Now, one more important point I want to discuss is encoding. Now, with this, I will be winding up the session for today. We will have the hands-on in the next session. Okay. Now, encoding. Now, while we discuss the last implementation, now there I have mentioned some one-hot encoding and label encoding. Now, what is that one-hot encoding and label encoding? So, just I will try to introduce here, and I will try to introduce some of the important terms which we will be mostly used in, or which will come across while we discuss the deep learning and the neural networks. Okay, so these things we will discuss for now, and we will wind up the session. Okay, now what is encoding means? Now you know that machine learning algorithms takes digits as the inputs. 150, 120, 150. So there will be different columns. Each column will have digits as the inputs, numbers as the input, maybe floating point, integer. Okay, so we will be taking the machine learning algorithms, and the neural networks also takes digits as inputs. But in some of the cases, some column or some features may contain some information like a male, a gender, male. If the column name is gender, it can contain male, female, male, etc. Now, how we can input these types of values to the machine learning algorithms? Now, we cannot give it directly. Some of the algorithm takes directly, but mainly we need to convert. Usually, we need to convert these. Uh, we can say categorical data. Okay, so we need to convert these category. See, category means female and male category. Okay, so usually we will come across a situation in which we need to convert categorical data into numerical format. Categorical data means female, male, etc. Okay, so you know that gender contains only three categories: female, a male, and sometimes may a transgender also comes into picture. For all the records, these three will be repeatedly coming: female, male, transgender, etc. etc. The same will be repeated again and again. Only three categories. So categorical data. Now we need to convert these categorical data into numerical format. Instead of this female male, now if we can have one for female, see, just a second. If you convert this female male into one or a zero for male, a one for female, and a two for transgender, it would be nice for a neural network to perform. Okay, so for that purpose, we need to have some encoding procedure. And usually, we will be using, or mainly, we will be using two types of encodings. One is one hot encoding, and the next one is a label encoding. Okay, one hot encoding and the label encoding are the main categories. So we have different other encoding schemes also, but I am limiting the discussion to only two types: one hot encoding and label encoding. What is the name for encoding? To convert categorical data into numerical form. Now, this is quite essential because in our previous session, also in our hands-on session, first hands-on session on neural network, there also we have used this encoding because. Uh, okay, so anyway, I'm not discussing it again. Okay, we will have one more hands-on session in a session. So at that time, I will explain what is the use of this encoding. For the time being, understand to convert categorical data into numerical format, we require this encoding. The first one is one hot encoding. Okay, now one hot encoding is a method of representing these categorical data as binary vectors like this. Okay, now assume that you have three categories of data: a red, green, blue. Or in our previous example, we have just now discussed male, female, transgender. So you have three categories of data. Now this male will be or red category will be encoded as 100. Green will be encoded as 010. Blue 001. So there are three vectors corresponds to three categories. Okay. If the first position is one means the first category. Second position is one means second category. Third position is one means third category. Okay. The corresponding position will be made one. Corresponding position will be made one. That's all. Now this type of encoding is known as one hot encoding. That's all. Okay. Now similar to this, okay, before that, what are the disadvantages of this one is, or what are the usages of this? Now, we will be using this one hot encoding uh, in scenarios where categorical values, have no ordinal relationship. So that means no order is there. If there is no order between these values, So order means it should come first, this should come second, this should come third. So this is the meaning of order. Now, usually, you know that in the previous discussion, the male and female, does they have any order in our data set? We have just now discussed. I told you in one of the column, assume that we have gender, and in that gender we have male, female, a transgender. Is there any order for this? No. Next one can be transgender again. Next one can be female again. It depends on the person, one and two. So there cannot be any order specified for this categorical value in this case. It depends on the record or the data available. There is no other order present there. In these situations, we can use this one hot and cold. That means if there is no order, inherent order between the categorical variables, we can make use of this one hot and cold. Usually employed for target variable in classification. So this we will discuss later. Now, while we discuss the the next, or while we will have the implementation in the next class, we will discuss it. Usually, in order to encode target variables, we will be using this one hot encode. So there is no such limitation, but usually we'll be using that. So the main thing is, if there is no inherent relationship between the categorical values, we can go for this encoding. That is one hot encoding. Now, next category is label encoding. Now, here, assume that you have the same data sets with the same categories: red, green, blue. Now, here, instead of giving a vector for each category, say here a vector, another vector for another category, another vector for another category, third category. Now, instead of giving a vector for all this category, we will be giving 0, 1, 2, a single number. Okay, so that means label encoding is a method of converting. Again, it's a method of converting categorical values into numerical values. Each category will be assigned a unique label, unique integer label. Okay, now red is assigned with 0, green is assigned with 1, blue is assigned with 2. Now, here, if this can be used if there is a particular order. Now, from this, you can see if there is a 0, 1, 2, then there is an order inherent, isn't it? 0, 1, 2, 3. Next one will be 3. Next one will be 4. So there will be an order. So if there is an order like this between the categorical variables, then the label encoding gives you good results. That's all. Now we can use interchangeably, but label encoder will give better result if there is a relationship between the categorical variables, or if there is a meaningful order between the, or among the categorical variables. We can use this label encoder. Okay, so these are the two types of encodings. Actually, this is quite simple. No need to worry about this. So when we have the hands-on, you can see that these things can be easily done with the help of Python coding. We have sklearn library available there. You can have all these things straight away. We can call the corresponding code for these encoding methods on sklearn library, and you can use it there. Okay, now encoding means, as a summary, encoding means converting categorical values into numerical digits. Two methods, two major methods: one hot encoding, label encoding. One hot encoding, we will have some vectors corresponding to each categories. There, the order of the categorical variables are not important. In label encoding, we will have single unique label for each category. Then the order, if it is important, if there is any order between the categorical values, then the label encoding gives better results. That's